Hey, welcome to the video. In this video, we're going to talk about how to solve a systems of inequalities word problem. This is also known as linear programming, so you can interchange those two phrases and you have basically the same type of problem. So let's dive right into it with our problem description. Okay, so we are screen printing t-shirts and sweatshirts to sell at the big game. And we have a few constraints that we have to meet. Okay, constraints basically that real people would have in real life. Limitations on how much time you have to get ready, how much materials you have, how much money you have. So taking a look at those, here's what we got. We have at most 20 hours of working time to make these shirts and sweatshirts. We have no more than $600 to spend on supplies. And in total, to make some money, we want to have at least 50 items to sell. Okay, the two items that we're creating, our t-shirts have just like one color of screen print. They're going to take 10 minutes to make. Supplies are going to cost $4. That's, the cost of the ink, the screen, I guess, and the t-shirt itself. But we're going to sell them so that we make a profit of $6. My guess is the total cost of the shirt is $10, but we should know that we're going to make $6 on each shirt. We're also going to have sweatshirts. Now, as you can see, the sweatshirts, they have three colors. We got a gold, a white, and a black that we're printing on there. They're going to take 30 minutes to make, and the supplies are going to be $20. Again, 3 inks, 3 screens, heavier material on a sweatshirt, but we're going to sell them for $40 and make $20 profit for each one that we sell. Okay, so if we're going to be printing those things, the question that we probably are already thinking is how many t-shirts and how many sweatshirts should we make so that we maximize our profit? Okay, we're going to make one assumption. We're going to assume that no matter how much we bring to sell, we're going to sell every single one of them. There's not going to be any left over. And we also want to know how much we're going to make in profit. Not just how can we maximize it, but what is that maximum value going to be? All right, so here is everything that we know so far. In order to get started with this, the first thing that we want to do is identify what our variables should be. So X and Y are pretty common, and whether you use the problem that they're asking at the end, how many t-shirts, how many sweatshirts should you make, or just what is the unknown, what don't we know yet? I would go ahead and make X and Y the number of t-shirts and sweatshirts that we're going to make. What we're going to start doing is using the information in the problem to write out what we'll later call constraints, limitations on what we can feasibly do. And the first one that is almost automatic with some of these situations, what values could those variables take? I can't make negative numbers of t-shirts or sweatshirts, so I'm going to say that X and Y both have to be greater than or equal to 0. If you look at the green sentence, the fact that we want to have at least 50 items to sell, we can write out another constraint that the number of t-shirts plus the number of sweatshirts needs to be greater than or equal to 50. If we use a combination of the orange line that we want to spend no more than $600 on supplies and the supply cost in red and purple, we can say that the cost of t-shirts, 4x, and the cost of sweatshirts, 20y, needs to be less than or equal to $600. Using the blue sentence, the time limit that we have at most 20 hours to make shirts. While looking at the red and purple again, the t-shirts are going to take 10 minutes to make, and the sweatshirts are going to take 30 minutes to make. So combined, they need to be less than 20 hours. Now, 20 hours is 1,200 minutes. So this time, 10x plus 30y less than or equal to 1,200. And I think that's all the limitations that we have. Again, we are calling these constraints. But we also want to write one more equation, and it's It's not a solved one. It almost has like a third variable to it. And we want to calculate or have an equation to calculate how much profit that we're going to make. Each of these word problems is going to have either a profit that we're going to maximize. It might be a cost that we're going to try to minimize, but there's some type of optimization going on. And the equation that we write that we are going to try to maximize or minimize will be called our objective function. Now, what we will do is develop we have a system of inequalities in our constraints, and we're going to develop a range of combinations of points that represent how many t-shirts and sweatshirts we're allowed to make, and use that to determine which ones maximize our profit. So, long story short, what we're going to do is create our system of inequalities graph. Well, let's dive into it and see what it looks like. We'll develop a set of steps afterwards. If we're going to create a graph, we need to be able to graph. And one of the ways that we do this is we make sure that our equations are in that slope-intercept form. I said equations, I should say inequalities. We want to make sure that if the inequality sign is going to flip or anything like that, that we account for it. So we can take, for example, our green equation. And we're starting with green because x is greater than or equal to 0 and y is greater than or equal to 0 in white. Those are already ready to graph. We got vertical and horizontal lines. But if we take our green equation and solve for y by, well, just subtracting x on both sides, now we're in that slope-intercept form. We can do the same with our orange equation by first subtracting 4x and then dividing by 20. And we should do the same with the blue equation by first subtracting 10x and then dividing by 30. These equations now kind of replace, they are equivalent to the like-colored ones in our original system, but now they're graphable. And the idea will be, let's go ahead now and make our graphs. First thing I should say is the top two in white, x is greater than or equal to 0 and y is greater than or equal to 0, they're just the x and y axis. So we are above the x-axis from our second inequality, and we are to the right of the y-axis in our first inequality. So I would just say, like, all these shadings are going to get a little bit cumbersome. Let's just assume that we're stuck in the first quadrant by those first two. And again, it's a very common thing when we're dealing with, like, fabricating t-shirts and sweatshirts. We can't have negative numbers, so we're stuck in the first quadrant. But if we graph the green one, we put our intercept at 50 and have a slope of -1, we would graph and get something like this. Because it's greater than or equal to, we shade up. This ensures us, this entire green region ensures us that we have at least 50 items to sell. If we graph the orange one on top of it, we get this line that has an intercept at 30 and a slope of -1/5. If we do the same with the blue one, we get this line. And they're both shaded down. Orange and blue are both shaded down because they were the constraints that said we have to spend less than, I believe, $600, and we only had a certain amount of time. So those are constraints that limit us. Now, again, the colors aren't wonderful, but if you are stuck in the first quadrant, below orange and blue and above green, the region that would have gotten shaded for this system of inequalities would be this one. And what it represents is every XY pair that is shaded in that region is a possible number of t-shirts and sweatshirts that we can produce that meets all of our constraints. That leaves us with at least 50 items to sell in the amount of time given and spending below or equal to the limit that we have. So that region is called the feasible region. It'll always be, at least with inequalities, linear inequalities, it's always going to be a polygon. And the possible answers, or the possible optimization points, are the vertices or the corners of this region. The way mine shook out, it ends up being a quadrilateral with 4 corners, and those are the possible points for either maximizing or minimizing our profit. All the other points can be produced, but they are guaranteed not to be the minimum or maximum. We want to go to the extremes if we want to make money, right? So I did graph this using Desmos, but if we had to do this by hand, we wouldn't be able to just, click on our lines or tap on our lines and find the intersection points. So how would we do this if we were making everything with pencil and paper? I need to find the coordinates for all 4 of those vertices, and they are all intersections of the lines that made up that system of inequalities. In other words, the first point is the intersection of the orange and green lines. So what I've done here at the bottom of the screen is I've taken those 2 inequalities and just made them equations. I'm not interested in which way we shade. I just want to know where the 2 lines cross. So I made a system of equations, and if I solve that, it will be the coordinates of that point. The second point, number 2, is the intersection of orange and blue. If I solve that system, I'll get that ordered pair. And then points 3 and 4 are actually a little bit easier to find. We don't have to solve a full system, although I guess we could write one. Those are the x-intercepts of the blue line, that's point 3, and the x-intercept of the green line, that's point 4. And as we know, we can find the x-intercept just by plugging in 0 for y into those equations. Let's start with the easier ones, 3 and 4. Focus in on equation 3. I want to plug in 0 for y, so I do so. And just a couple of steps, I can subtract 40 on both sides and multiply by -3. And it turns out that x is 120, so that point is 120, 0. Equation 4 is going to work the same way, or point 4 I should say, is going to work the same way. We're plugging in 0 for y, and just by adding x to both sides we get x is 50, so that point is 50, 0. For the other 2 equations, starting with equation 1, or system 1, to find point number 1, we're going to solve this system, and it's already solved for y, so I'm going to use the substitution method, and that's the one where I am basically here writing out the green equation and replacing y with the expression that y is equal to in the orange one. It's going to work out this way pretty frequently if you solve for y to graph them first, so it's a good option. But to solve this, I could add x to both sides, or add 1x to both sides. Remember, 1 is 5 over 5, so common denominator, I get 4/5 x. Let's also subtract 30, and then multiply by the reciprocal of 4/5, 5 over 4, and we'll get x is equal to 25. At this point, I know that the ordered pair is going to be 25 comma something, and I could choose either of those original equations in green or orange to plug into. I'll choose green just because it doesn't have a fraction. If I plug in 25, I get y is 25, and that makes my point 25 comma 25. And we'll basically just repeat the same thing with equation, or rather point 2, system number 2, whatever you want to call it. I'm going to write the orange equation and replace the y in the orange equation with the expression in the blue one. It's going to look like this, same as what we did for the first point. This time, to add 1/5 x to both sides, I do have to find a common denominator of 15, and I would get -2/15 x. I'm going to subtract 40 on both sides and multiply by the reciprocal, negative 15 over 2 on both sides. I get x equals 75. Now, I may have had another way that I can make this easier on myself, but I did it this way and I got x equals 75. That's my first coordinate. And now that I have that, I'll just plug it into either of those equations. I don't know why I chose the blue one, but I did. I'm plugging in 75, and that tells me that y is 15. So that ordered pair is 75, 15. Just make sure if you solve for x first, it's the first coordinate, but if you solve for y first, it is still the second coordinate. So these 4 points now represent my potential answers. If you remember, x represents the number of t-shirts and y the number of sweatshirts. So point number 1, 25 of each. Point number 2, 75 t-shirts, 15 sweatshirts, and so on. Back on our graph, this is what it would look like. Don't forget that these are the vertices, the corners of our feasible region, and they are the potential answers or potential optimization points for either minimizing or maximizing our profit. To see which one is the winner is literally just plug in those XY pairs into the profit function. So I'll start with 25, 25. If I plug in 25 for X and Y and simplify, I get 650. That corresponds with making 650 bucks. Okay. If I up the number of t-shirts and decrease the number of sweatshirts and use that 75-15 point, when I plug it in, I get 750. So that's a way that we can make more money. I think it's pretty obvious that this next one's not going to work for us because making 50 t-shirts and 0 sweatshirts cannot possibly net us more money than making 120 and t-shirts and 0 sweatshirts like the next point. But it actually probably minimizes how much money we can make if we wanted that kind of thing. But the question is, what if I just made t-shirts? All 120 of them would sell for just shy of the 75-15 point. Here we're only making $720. So 750 is our maximum. That means making 75 t-shirts and 15 sweatshirts is the best way to optimize our money, to make the most. Now, looking at this thing, where do we start? Where are we now? We had our description of our problem with all those written constraints about time, money, and how many items we have to sell. We wrote out a series of constraints, made them graphable by changing them into slope-intercept, and plotted them, gave us a feasible region, the vertices of which we calculated and listed as possible min or max points. We plugged those into our objective function for profit, and then figured out which of those points, not only what the maximum profit was at 750, but which point gave us that, and that was 75-15, or 75 t-shirts and 15 sweatshirts. As always, we solution in terms of the problem given. So the question was, how many t-shirts and how many sweatshirts should you make? And then what is your maximum profit? Well, the first question, we will earn the most profit when we sell 75 t-shirts and 15 sweatshirts. And the maximum profit from selling these items will be $750.